count and say. The problem is to generate the nth string in the count and say sequence. Each string in the sequence describes the previous one using run-length encoding. The input is a single integer n, where n ranges from 1 to 30. The output is a string that represents the nth term in this sequence. To solve the problem, first, check if n is out of bounds. If it's less than 1 or greater than 30, we throw an error. If n equals 1, return the string 1. This is the base case. Otherwise, recursively call the method with n-1 to get the previous term in the sequence. Initialize a variable to hold the first digit of the previous result. Also set up a counter to track how many times that digit appears consecutively. Use a string builder to construct the result for this level. Loop through each character in the previous result starting from index 1. If the current character matches the previous one, increment the counter. If it doesn't match, append the count followed by the digit to the string builder, then reset the counter and update the digit. After the loop, append the final count and digit to the result. Return the string builder as a string. Edge cases include ensuring that the base case is properly returned for n equals 1, and that we always append the final count and digit after the loop ends. Complexity. Time complexity is O of m times n, where n is the input and m is the average length of intermediate strings. Space complexity is O of m for building the string at each step. Random pick with weight. This problem asks us to randomly select an index from an array of weights, where the probability of choosing a particular index is proportional to its weight compared to the total. The input is an array of positive integers, and the output is an integer index selected according to the described probabilities. To solve this, we take the following steps. First, we compute a prefix sum array called sum, where each element represents the total weight up to that index. We initialize sum such that sum 0 equals the first weight. We loop through the rest of the array and set sum I to be sum I-1 plus w I, the weight at the current index. This transformation makes it easy to treat the weights as ranges in a number line, where picking a number within this total weight range simulates the intended probability. Next, in the pickIndex method, we generate a random integer between 1 and the total weight inclusive with random. NextInt. Note random. NextInt is exclusive on the upper bound, so we need to add 1 to ensure inclusivity. After generating the random number between 1 and the total sum of weights, we use a binary search to determine which index to return. Here's how the binary search works, step by step. First, we initialize two pointers, start at 0 and end at the last index of the prefix sum array. We then enter a loop that continues as long as start is less than or equal to end. In each iteration, we calculate the midpoint by taking the average of start and end. We then compare the value at the midpoint in the prefix sum array with the random number we previously generated. If the value at the midpoint is greater than or equal to the random number, it means that this index might be a valid result. However, we want to find the first index that satisfies this condition, so we move the end pointer to one position before the midpoint. If the value at the midpoint is less than the random number, it means that the result must lie to the right. So, we move the start pointer to one position after the midpoint. Once the loop exits, the start pointer will point to the smallest index in the prefix sum array, where the value is greater than or equal to the random number. This is the index we return as our result. Complexity. Time complexity is log n per pickIndex call, where n is the number of elements, due to binary search. Space complexity is linear in n for storing the prefix sum array. Make in a large island. We are given a square binary matrix where each cell is either 0 or 1. We can flip at most 1 0 to 1. The goal is to return the size of the largest possible island we can form by doing that. An island is defined as a group of ones that are connected either up, down, left, or right. Input, a 2D grid of size n by n, filled with binary values, that is, zeros and ones. Output, an integer representing the maximum area of an island we can obtain by flipping at most 1 0 to 1. To solve this problem, we follow these steps. First, determine the height and width of the grid using the grid's length. Create a map called ID to island size. This will associate each unique island ID with its corresponding area. Create a list called 0 positions. Begin scanning every cell in the grid using nested loops. For each cell that contains a 1, we will label the entire island that this cell belongs to using a helper method called BFS label island. In the BFS label island method, we pass the grid and a starting position, which is a coordinate in the form of row and column. Inside the BFS method, we initialize an integer variable called area to 0 and a queue to perform a breadth first search. We mark the first cell by giving it a new ID calculated as row multiplied by the grid length plus column plus 2. This unique ID ensures we distinguish between different islands. As we perform the BFS, we scan all 4 directions up, down, left, and right. If the neighbor cell is A1, we convert it to the same island ID and add it to the queue. We increment the area as we visit each cell. Once the BFS completes, we store the calculated area in the map using the island ID as the key. While scanning the grid to do BFS for cells containing 1, we also record the positions whose original cell value are 0. Note, as we already modified the grid cell values, we can't simply check if the cell value is 1 and then do else. We must explicitly check else if the cell value is 0. Coordinates of zeros are added to the 0 positions list. Initialize a variable called max to store the maximum island size found so far. After all islands have been labeled and stored in the map, we scan the grid again. This time, we look for zeros recorded in the 0 positions list. For every 0 found, we simulate flipping it to a 1 and calculate the total area of the connected islands around it. To do this, we again check all 4 directions. If a neighbor cell has an island ID greater than 1, meaning it's part of an island, and we haven't counted this ID yet, we add its area to a local size counter. We use a set called visited to ensure we don't double count the same island ID from different directions. Finally, we update the maximum area by comparing it to the local size. At the end, the maximum recorded area is returned as the answer. This approach covers edge cases such as: if the entire grid is already filled with 1s, no flip is needed. If the grid contains only zeros, flipping any one of them creates a single cell island. Attention! The ID is generated by using the formula row times grid length plus column plus 2, so that during BFS we can differentiate visited island cells versus unvisited ones, whose original values are 0 or 1. Complexity. The time complexity is big O of n squared, where n is the size of the grid, because we potentially visit every cell multiple times, once during labeling, and again while checking for maximum size. The space complexity is also big O of n squared, due to the use of additional data structures such as the map, 0 positions list, and the visited set. Convert binary search tree to sorted doubly linked list. We are given a binary search tree and asked to convert it to a circular doubly linked list in sorted order. Each node should be modified in place so that its left pointer acts as its previous node, and its right pointer acts as its next node. The final structure should be circular, meaning the smallest node points back to the largest, and the largest node points forward to the smallest. Input, a binary search tree where all values are unique. Output, the smallest node of the circular doubly linked list. To solve this problem, we follow these steps. First, check if the root of the binary search tree is null. If it is, return null because there are no nodes to link. Create a dummy node with value -1. This dummy node will help us handle the head and tail linking more easily. Use a stack to perform an in-order traversal of the tree. In-order traversal naturally visits nodes in ascending order for a binary search tree. Define a stack. Define a helper function called pushLeft. This function takes a node and a stack. Then repeatedly push the node and all of its left descendants onto the stack as long as they are not null. Call pushLeft against the root of the binary search tree. Initialize a variable called previous to point to the dummy node. This will help us connect the current node to the last processed node. Enter a loop while the stack is not empty. In each iteration, pop the top node from the stack and call it current. Set current's left pointer to previous. Set the previous node's right pointer to current. Update previous to be the current node. Call push left on right child of current node. After processing all nodes, connect the tail of the list to the head by setting the previous node's right pointer to head's right, and head's right's left pointer to previous. This completes the circular linkage. Finally, return head's right, which points to the smallest node in the list, effectively the real head of the doubly linked list. Complexity. The time complexity is big O of n, where n is the number of nodes in the tree, because each node is visited exactly once. The space complexity is big O of n in the worst case due to the usage of a stack during in-order traversal. Convert sorted array to binary search tree. We are given a sorted array of integers in increasing order. Our goal is to convert this array into a height-balanced binary search tree. This means we want a tree where the depth of the left and right subtrees of every node is as even as possible. Input, a sorted array of integers. Output, the root node of a height-balanced binary search tree. Here's how the solution works, step by step. We define a method called buildBST that takes three parameters: the input array, a start index, and an end index. This method builds and returns the root of a binary search tree from the elements in that range. The base case is simple. If the start index is greater than the end index, we return null. This means there are no elements to convert in that range. Next, we calculate the middle index using the formula, start plus end divided by 2. We use this middle index to maintain balance, so the left and right halves of the array get distributed evenly. We then create a tree node using the middle value as its root. To build the left subtree, we recursively call the buildBST method on the left half of the array from start to mid -1. To build the right subtree, we call the buildBST method again, this time on the right half from mid +1 to end. Finally, we return the root node created from the middle value, which now has both left and right children connected. Complexity. The time complexity is big O of n, where n is the number of elements in the array, since we visit each element exactly once to create a node. The space complexity is big O of log n due to the height of the recursion stack in the best balanced case. The returned node number should be of big O of n as we are returning a tree of size n. Convert sorted list to binary search tree. The problem is to convert a sorted singly linked list into a height-balanced binary search tree. Input. The head of a singly linked list where values are sorted in increasing order. Output. The root of a binary search tree that is height-balanced, meaning the depth of the two subtrees of any node never differs by more than 1. Solution 1, O(n log n complexity. To solve this problem, we need to build the tree recursively, always choosing the middle element of the current list as the root. This ensures the tree remains balanced. Since it's a singly linked list and not an array, we cannot access elements directly by index. So, we must walk through the list to find the middle node. Here's the step-by-step breakdown. Step-by-step solution. Step 1, if the head is null, we return null. This is our base case. If the input list is empty, there is no tree to build. Step 2, call a helper method named getNode before mid. This method finds the node that comes just before the middle node of the list. It uses the slow and fast pointer technique. Create a dummy node pointing to the head. Let's call this dummy node before mid. Use 2 pointers. The fast pointer moves 2 steps at a time, and the slow pointer moves 1 step at a time. Initially, both slow and fast point to the head. The dummy node is ahead of slow by 1 node. While fast can move 2 steps forward, move slow 1 step and fast 2 steps. Also update node before mid to be the current slow. When the loop stops, slow will be pointing to the middle of the list. And node before mid will be right before that. Return the node before mid from this method. Step 3, now in the main function, create a new tree node using the value at the middle node. This middle node is node before mid.next. Step 4, recursively build the right subtree using the second half of the list, which starts from node before mid.next.next. Step 5, disconnect the right half by setting node before mid.next to null. This prevents it from being reused or causing cycles. Step 6, check if the middle node is the same as the head. If it is, that means there is no left part of the list, so the left child should be null. Step 7. Otherwise, disconnect the left half by setting node before mid dot next to null. Then recursively call the function to build the left subtree from the first half of the list. Step 8. Finally, return the root node, which now has both left and right children built from the two halves of the list. Attention! The helper method getNode before mid uses fast and slow pointers to identify the middle node of the list in linear time. In this method, we made a dummy head node so that we will never return null. Then since its input won't be null, it's safe to directly call the next of the returned node, which is the one before the mid node of the given list. By returning the node before mid instead of the mid node itself, we make it easier to split the list into two halves by modifying the next pointer. The check to avoid building the left subtree when the mid is the head ensures we do not recurse infinitely on the same node. Complexity. The time complexity is big O of n log n. Each recursive level processes all nodes to find the middle, and there are log n levels because the list is split in half each time. The space complexity is big O of log n due to the recursive stack depth for building the tree. Solution 2, O(n) complexity. In solution 1, the tree is built from the root down to the leaves. In contrast, solution 2 builds the tree from the leaves up to the root. The key idea is to insert nodes into the binary search tree in the same order they appear in the linked list. This allows the entire tree to be constructed in linear time, that is, O of n. Throughout this process, the list head pointer is advanced during each recursive step, ensuring it always points to the correct node for the current root. Here is the step-by-step breakdown of how the solution works. First, we determine the total number of nodes in the linked list. This is done using a helper method called getLen, which loops through the list and counts the nodes one by one. Next, we wrap the head of the list inside a one-element array called h. This is done because in Java, objects passed by reference are mutable. By wrapping the head in an array, we ensure that updates to the head pointer within recursive calls will persist across all levels of the recursion. The core logic lies in the recursive method in order builder, which takes the one-element array h containing the list node being visited and updated, and two integer parameters start and end. This method constructs the binary search tree in an in-order fashion, meaning we recursively build the left subtree, then the current node, and finally the right subtree. For each recursive call, we calculate the midpoint of the current range using the formula mid equals average of start and end. We recursively build the left subtree from the start to mid minus 1. Then we create a new tree node using the current value of the head node from the list. We then move the head pointer one step forward. Note here, as the list node is passed through the one-element array h, we need to update the first element of it. Finally, we recursively build the right subtree using h, mid plus 1, and end as input of the in-order builder method, and attach it to the right of the current node. We call this recursive helper method with the input head in the list, 0 as start and length minus 1 as end, and return its output. Complexity. Time complexity is big O of n, where n is the number of nodes in the linked list, since each node is visited exactly once during in-order construction. Space complexity is big O of log n, due to the recursion stack used for building a balanced tree. Longest common subsequence. We are given two input strings, text1 and text2. The task is to find the length of the longest sequence of characters that appear in both strings in the same relative order, though not necessarily consecutively. Input, two lowercase strings, called text1 and text2. Output, an integer, the length of their longest common subsequence. Here is the step-by-step explanation of the solution. First, we handle the edge case. If either input string is null or has 0 length, we immediately return 0 because no common subsequence is possible. Next, we calculate the lengths of the two strings and store them in variables len1 and len2. We define a two-dimensional array named dp with 2 rows and len2 plus 1 columns. This array will hold the length of the longest common subsequence found so far. dpij stores the longest common subsequence for the first I characters for the first string and the first j characters for the second string. Instead of defining a dp matrix of size len1 plus 1 by len2 plus 1, we use only 2 rows instead of the full matrix to save space, since we only need the previous and current row at any time. We loop through the first string from index 0 to len 1-1. This is the outer loop. Inside that, we loop through the second string from index 0 to len 2-1. This is the inner loop. If the character at the current index in text 1 is equal to the character at the current index in text 2, then we set the value at dp I plus 1 modulo 2, j plus 1, to be dp I modulo 2, j plus 1. This means we have extended a common subsequence by one character. If the characters do not match, we set the value at dp I plus 1 modulo 2, j plus 1, to be the maximum of 2 values. The value to the left in the current row, which is dp I plus 1 modulo 2, j, and the value above in the previous row, which is dp I modulo 2, j plus 1. This ensures we carry forward the best result found so far, by dropping either ith char in the first string or jth char in the second string. After both loops finish, we return the value in dp len 1 modulo 2, len 2, which holds the length of the longest common subsequence. Complexity. Time complexity is big O of n times m, where n is the length of text 1 and m is the length of text 2. Because each cell in the dynamic programming table is visited once. Space complexity is big O of m, because only 2 rows of size m plus 1 are used at any time. Valid palindrome. We are given a string and need to determine whether it is a palindrome. A palindrome is a string that reads the same forwards and backwards, after removing all characters that are not letters or numbers, and after converting all letters to lowercase. The input is a string called s, and the output is a Boolean value, either true if the string is a valid palindrome or false otherwise. The algorithm uses a 2-pointer approach to check characters from both ends of the string. Here is the step-by-step explanation of the solution. First, we check if the string is null or if its length is less than or equal to 1. In either case, we return true because it's trivially a palindrome. We initialize 2 pointers, start at 0 and end at the last index of the string. We loop while start is less than end. Inside the loop, we move the start pointer to the right until we find a character that is alphanumeric. We use a helper method called isAlphanumeric_char to check this. The method isAlphanumeric_char returns true if a character is a digit or a letter, including both lowercase and uppercase. Similarly, we move the end pointer to the left until we find another alphanumeric character. We then convert both characters to lowercase using a helper method called convertToLower. The method convertToLower manually converts an uppercase character to lowercase by subtracting the difference between uppercase a and lowercase a. If the character is already lowercase or a digit, it is returned unchanged. If the lowercase characters at the start and end pointers do not match, we return false immediately, since it is not a palindrome. If they do match, we move both pointers closer towards the center, incrementing start and decrementing end. If the loop completes without a mismatch, we return true, which means the string is a valid palindrome. Complexity. The solution runs in linear time, big O of n, where n is the number of characters in the input string. The space complexity is constant, big O of 1, since we are only using a few variables and not creating extra data structures. Valid Palindrome II. The problem asks whether a given string can be turned into a palindrome by removing at most one character. A palindrome is a word that reads the same forwards and backwards. The input is a string made up of lowercase English letters. The output is a Boolean value, true if the string can be converted into a palindrome, with at most one deletion, otherwise false. The solution is to invoke a helper method named isValidPalindrome recursively. It takes 5 arguments. The first parameter, s, is the original string being checked. The second and third parameters, start and end, represent the current range of the substring being analyzed. The fourth parameter, detected mismatches, is a counter for how many mismatches we've encountered so far. The fifth parameter, allowed mismatches, sets the maximum number of mismatches we're willing to tolerate, which is 1 in this problem. Inside the helper method, a while loop checks characters at the start and end pointers. If they match, we move the start pointer forward and the end pointer backward. This continues until the characters do not match or the pointers meet. If the loop finishes and the pointers have crossed, we return true, because that means the remaining substring is a valid palindrome. If a mismatch occurs, we increment the mismatch counter. If it exceeds the allowed mismatch count, we return false. Otherwise, we recursively check two new substrings. One excluding the character at the start index. We check it by calling isValidPalindrome with input s, start +1, end, detected mismatch, and allowed mismatch. And the other excluding the character at the end index. We check it by calling isValidPalindrome with input s, start, end -1, detected mismatch, and allowed mismatch. The method returns true if either recursive call returns true. This helper handles all logic for comparing substrings, and allows flexibility for future cases where more deletions might be allowed. To answer if the input s is a palindrome with at most one delete, we call the isValidPalindrome helper against the input string s, 0 as start, length -1 as end, 0 as detected mismatch, and 1 as allowed mismatch. Complexity. Time complexity is big O of n, where n is the length of the input string, because we traverse the string only once in the average case. Spatial complexity is O1. More generally, if we allow up to k mismatches, instead of 1, the recursive approach has a worst-case time complexity of big O of 2 to the power of k multiplied by n over k, due to branching at each mismatch. If k equals 1, this is 2 by n. If k equals n, it degrades 2 to the power of n. The space complexity is big O of k due to the depth of the recursive call stack. If k equals 1, it will be O1. When k equals n, it will be On. Valid Palindrome III. We are given a string and a number k. Our goal is to determine whether the string can become a palindrome by removing at most k characters. Input, a lowercase string s and an integer k. Output, a Boolean value, true if the string is a k palindrome, otherwise false. Here we can basically reuse the solution from Valid Palindrome II. However, when k is large, we may see timeout due to temporal complexity of big O of 2 to the power of k multiplied by n over k. Inspired by the solution of longest common subsequence, below is the O(n) squared solution. Here is the step-by-step explanation of the solution. First, we reverse the original string by iterating from the end of the string to the beginning, and appending each character to a string buffer. We convert this reversed buffer to a new string, which we call rev. Then, we compute the longest common subsequence between the original string s and its reversed version rev. Since a palindrome reads the same forward and backward, finding the longest subsequence that appears between the string and its reverse gives us the length of the longest palindromic subsequence. If the length of the longest common subsequence plus k is greater than or equal to the original string's length, then we return true. This means we can delete at most k characters to make it a palindrome. The solution for longest common subsequence is used to compute the length of the longest common subsequence between two strings. Complexity. Time complexity is big O of n squared, where n is the length of the string, due to the nested loops in the dynamic programming table. Space complexity is big O of n, because we use only 2 rows in the DP table at any time.